Section 6.4, the gradient descent method. Here is the problem we want to solve in this section. Omega is a subset of Rn. For a given real valued function f, the general minimization problem is formulated in this way. Try to find the minimum of f when x is in the set omega. In this context, f is the objective function. Sometimes it is called the loss function or the cost function. And omega is the domain of the function and the constraint set. We'll try to solve the minimization problem iteratively. Given an initial guess x0, we'll try to find successively approximations xk of this form. The new approximation is corrected by this correction term. Here pk is the search direction and gamma k is the step length. After finding the direction, and we try to decide this step length. The gradient descent method is also known as the step-based descent method, or sometimes it's called the Richardson's method. Here, for this type of iterative algorithm, and we try to derive the gradient descent method here. When xk plus 1 is decided with this the correction, then here we may try to use Taylor expansion for this perturbation. So f of xk, and that is gradient of f and dot the search direction, and along with a scaled with a step length, and second order term of gamma k. Now, once we assume the second derivative, the Hessian, is bounded, then we can write in this way. The goal is, now this term must be smaller than that term, so that it is the descending, the value is descending. Okay, that's the goal. And once, okay, this dot product is negative, then because this step length is positive, we have the smaller value when, okay, this is sufficiently small, or, and the second derivative, the Hessian, is non-negative. Now here our choice is for pk, the search direction, we try to use negative of the gradient. Then this dot product is the same as negative of the gradient norm squared. So it is negative when the gradient is non-zero. So that's the choice for the gradient descent method. So here we can summarize. In the gradient descent method, the search direction is the negative gradient, the step is the descent direction. Okay. Now we'll try to analyze the method in 1D. Consider the minimization problem in 1D, the minimization of f of x when x is in a set S, and S is a closed interval in the real line. Then the gradient descent method can be formulated in this way. Xk plus 1 is xk minus gamma and f prime at xk. That is the derivative minus derivative is minus the gradient. Okay. Now we'll try to set the step length gamma very effectively. Here we start with Taylor theorem, and f of xt, x plus t, for general x and t, we have f of x plus t f prime at x, and this remainder is integral form. But you can use for this one the Lagrange remainder. That is, for this portion, you may use here, that is t squared over 2 f double prime at some point. Right? Okay, either this way or that way, you can use the remainder term, express the remainder term. Now, assuming that the second derivative is bounded and bounded by L, then we have here f of x plus t is bounded by f of x and that term, and we are choosing maximum from this one. So it is t squared over 2 and maximum value of that one, L. Now for this formula, now we are using here x is xk and t is minus gamma f prime at xk. Then we have here, this term is bounded by the right side along with these terms we have here. Now that is the same as this one. Now the goal is, that is, this portion is positive, then this will be strictly smaller than this value. So that's squared, and once the derivative is non-zero, then if this term is positive, then it can happen. So the requirement is this one, and that is the same as here. The gamma is between 0 and 2 over L. This quadratic term has a maximum when the gamma is the midpoint. So yes, gamma is 1 over L. You can get this one here by using the derivative technique. For this one, try to make a derivative and set it 0, then you can find this equation also. Okay, now here the effective gradient descent method can be written in this way. And that is the formula along with the gamma 1 over L. We have that. That is here. And furthermore, we can get this one from that one. Now, when the gamma is 1 over L, we can rewrite this one here in this way, so that this new value is bounded by old value minus gamma of 2 f prime at the old the point squared. So we get this inequality that will be used later on for the deciding this gamma. But in 1D, theoretically, we can choose this value, but in general, it's not easy to set this value. So that when we try to find a good, reasonable parameter step length, and we have to find the value such that this inequality is satisfied. That'll be used later on. Here we have a convergence analysis. You can read this, the remark, but here the main idea is here. Once xk converges to x hat, then at x hat, the limit, the f prime, the derivative is 0, which means that x hat is a critical point. And again, that means that the gradient descent method is trying to find a critical point, so local minimum and or saddle point, and finding global minimum is not here analyzable. But anyway, and here the algorithm is trying to find a local minimum. It can be the global minimum, but anyway, around the point initial value, it tries to find local minimum. For example, the objective function is given pictorially like that. Then once you start from here, then it will go down and reach that one. So x hat in x direction will be this one. Once you start from here, then it will go down and x hat will be that one. So in any way, the algorithm is trying to go down in function value and reach at a local minimum. Okay, now we'll continue in the second part. Thank you.